All right, so given the Laplace transform we learned in the previous video, we kind of have some intuitive properties here. And the first one to know is that if you take the Laplace transform of a sum or difference of two functions, you're going to end up with the sum or difference of the transforms. And that's because the transform is basically an integral, and we know integrals you can split up by adding and subtracting. Now, the other one is if you have the Laplace transform of a constant multiple of a function, whose transform you know, basically the constant multiple can just come outside. So let's look at this with the next couple examples. So the Laplace transform of 3 plus 2t. Well, I know that that's going to be the Laplace transform of 3 plus the Laplace transform of 2t. Now, I know what the Laplace transform of t is, so I'm going to go ahead and write that as the Laplace transform of 3 plus 2 times the Laplace transform of t. Remember, the Laplace transform of 3 was 3 over s, and the Laplace transform of t was 1 over s squared, and if we're multiplying by 2, there's the Laplace transform of that function. Okay? Now, moving ahead to this next one, now notice it's not exactly in a form of a function whose transform we know, but we can do algebra to this. So we're going to multiply t to the third times 4 minus 4t plus t squared, and that's going to get us 4t to the third minus 4t to the fourth plus t to the fifth. So then that means that the Laplace transform, which I'm just going to write as big F of s, is, well, let's see. It's 4 times the transform of t to the third, which is 3 factorial over s to the fourth, minus 4 times the transform of t to the fourth, which is 4 factorial over, s to the fifth, and then plus the Laplace transform of t to the fifth, which is 5 factorial over s to the sixth. And of course, we'll clean these things up because these numbers are manageable. 3 factorial is 6 times 4 is 24. So that's 24 over s to the fourth, minus 4 factorial is 24 times 4 is 96 over s to the fifth. And then plus 5 factorial is 120 over s to the sixth. And there's our transform of that second function. Looking at the third one, notice we have exponentials. Remember that the Laplace transform of e to the at is 1 over s minus a. So that means that our Laplace transform is, well, let's see. There's a 2 out front, so I'm going to be multiplying a transform by 2. 2 times 1 over, that'd be s minus negative 3, which is s plus 3, minus the Laplace transform of e to the negative 5t is 1 over s minus negative 5, which is plus 5. And you can write that as 2 over s plus 3 minus 1 over s plus 5, which you could also combine and write into one fraction, find the lowest common denominator, etc., etc. There's no need to do that here. And then for the last one, Laplace transform of sine and cosine, we're on it. So that means that the Laplace transform of g of t, which I'm just going to call big G of s, is 4 times the transform of sine minus 2 times the transform of cosine. Sine was a, in this case 2, over s squared plus a squared, which is 4. Cosine is s over s squared plus a squared, a here being 3, so that's 9. And that would be 8 over s squared plus 4 minus 2s over s squared plus 9. And again, same story with this one. You could create a common denominator and combine the fractions and write your answer as one entire fraction, which would be acceptable as well, but there's really no need to do that at this point. In fact, if you kind of infer what's going to happen, we're going to get to a point where we're going to say, here's the transform, find me the function that this came from, and it turns out that this form is convenient more so than the combined form. So you might see some familiar ideas coming back about breaking apart fractions. I wonder what he's talking about. Anyway, that's how you find Laplace transform of some combinations of functions. Thanks for watching.